we have started this program almost three years ago, and last 1 year, to make it more effective and more collaborative with the industry versus academia, we are now jointly working with all the universities, and then we are requesting them to start. I mean, to host this session, so that the students are can take more out of these sessions, right? And so in NXP, maybe for everyone information, we have 4 locations in India, right? So Noida, Bangalore, and then we have Hyderabad and Pune as well. So we have expanded it a lot in the last couple of years, and uh, I think worldwide, we are working on many aspects of the different SOCs, right? And uh, what we found is these sessions are more effective, and let's say people are. I would request everyone to gather their questions and post it on the chat, so we will try to address at the end of the session. And our speaker today is well-known person in industry as well as within NXP. And as you see that today's topic is very much relevant to the real device. Once we get the silicon back, how what other things is to be done on this, right? So Anirudh will speak on this topic, and so I would like to hand over to Professor, and please say a few words about from your side.
Thank you, Mr. Amit. Thank you very much. And good evening, everyone. I'm Dr. Manoj Kumar Pandey, Director of MIT School of Engineering and Technology. And on the outset, on behalf of this school, I would like to welcome you all to the NXP Campus Connect session. And it is my proud privilege to host this flagship program of NXP India that aims towards building the future innovators and creative thinkers. To say a few things about the MIT is the group of institutions has established 11 universities and 125 institutions, 25 preschools, and having more than 200,000 students, and having campuses in India, abroad, including campus in London, New York, California, Singapore, Dubai, Mauritius, and many more. And we are offering a vast group of researchers are there, those in the various areas, in the field of engineering, in the field of public health, virology, immunology, and many more. And we have more than 6,000 plus faculty members, and uh, and best of the art laboratories around. So at MIT, we have been ranked among the top 3% universities globally, as per the QS MIT ranking released in 2023, and awarded A plus grade by NAC. And we believe in a strong industry academia collaboration. That's why today's program is being conceived. And we provide win-win situation opportunities for both the academia and industry as well. So for the students, we used to provide the industry exposure, and for the industry, the young people, the trained, the skilled, semi-skilled, those who are going to solve some of their real-time problems, business problems, and all. Uh, you all know that today's session is about the test product engineering and automated test equipment engineering. Uh, just to tell about the glimpse of the topic that, although Mr. Anirudh is going to highlight on more on that, this test equipment, this ATE is a technology. This is used in manufacturing, quality control to access the functionality and the performance of semiconductors, especially in FPGAs, in CPLDs, SoCs, and all. And this ATE that automates the testing processes, which will increase the efficiency, the accuracy, and many more that is uses in the semiconductor testing. And as said by Mr. Amit very well, by because the semiconductor is now silicon is going to be in a huge way, and testing is important to ensure the quality, the reliability, the performance of the semiconductor device. And moreover, we now all believe on the quality. It ensure about the compliances, the industrial quality standards and fault detections. It will detect defects as well, because most of the, I mean, if you take the complete lot of the semiconductor chips, then the defected chip is always being a problem for the world. It will ensure that every chip that is being fabricated, that meets the highest standard of the reliability and the functionality as well. We all understand that the semiconductor technology and the packing density, rather, that packing density is increasing every day, and hence that the functionality is being increasing. So with the increasing functionality, packing density, the complexity of this is increasing, and we all know that still it is going on as per the Moore's law, which says that after every maybe 5 years, the packing density will double and the complex size is going to be reduced. So we are going to moving towards the nano size, and then putting more and more functionality into it. So in that sense, the testing is becoming very, very important, and the important impact of the semiconductor testing techniques also increasing. So it will also directly impact the semiconductor manufacturing, as the goal is always to ensure the high yield. And you know that now the government of India is also promoting, supporting, and in many way how we can better use of the semiconductor and its technology. So with this, I think just to say something about the speaker today of this afternoon, I would like to introduce the speaker, Mr. Anirudh Sachan. He's a senior principal test engineer at NXP Semiconductors, and he has more than 2 decades of experience in leading and building teams for pre and post silicon validations, ATE for automotives, edge processing, and networking of SoCs. So after working for close to 10 years in free scale semiconductors, and it's a very, very important, and free scale semiconductor is somewhere which very few people is working on that. And Mr. Sachin, that he moved to NXP Semiconductor and is currently working as a senior principal test engineer. So with this, I welcome Mr. Sachin and the whole team, and request him to share his experience, his test products engineering, automated test equipment engineering, and all those which are been very, very important for the student to know, especially in the field of semiconductor. And I must say that the semiconductor is coming in a huge way, and the word is waiting towards, and NXP is one of the organization which is apart from all these things is hugely working on the semiconductor. And Mr. Anuruddh, this topic will be of more important to me because I also belongs to the semiconductor devices. My research was in the semiconductor devices in a miniaturization, where we had been conceived and conceptualized the giga range devices for the semiconductor in the nanoscale we have done with the huge number of packing density of huge number. And so this will be very, very interesting for me as well, because we also face a lot of problem while, because in India we do not have too much fabrication facilities. So at that time, so now, yes, the NXP is doing wonderfully incredible task in the semiconductor. My appreciations and my approval to all the team of the NXP. With this, over to you, Mr. Anuruddh. Thank you very much.
Thank you, Professor, for the introduction. Thank you, Amit. So let's start the topic. So I think with the, I mean, well said, Professor. So India is kind of becoming a new semiconductor manufacturing, test engineering, and assembly hub, with recently many company announcing their uh, factories or productions in India. So test engineering was kind of not a very well-known topic till many, many years in India. So it will basically have very huge demand in next.
You had been muted, Mr. Anuruddh. Kindly unmute yourself.
Yeah. Okay.
Yeah.
Sorry about it. So I mean, test engineering, as India semiconductor ecosystem is increasing in the test and assembly domain. So I think it becomes a very interesting topic in coming years with lot of jobs and lots of in this particular testing and assembly space. So which was kind of not very limited people and limited companies were in this field. So it will become a very important topic for next few years. So I will start the presentation without much delay. So let me share. Well, I'm already sharing, I think.
Yes, now it is visible.
Now it's visible. Okay, just give me a second.
Yes, slides is visible, but it's not in a slideshow mode.
Yeah, I'm just okay. So good to start. Everybody can see it.
Yes.
Okay. So today agenda will be why to test. I mean, because a lot of people see the verification design, then people think why do we test the final products? And then overview of ATE. What is exactly the ATE is? Uh, Next topic will be test interface hardware and equipment. Then manufacturing test flow. Actually, how once you design the product, what is the full picture when you get the parts? And then what are the testing voltage we test and design changes to support the ATE? I mean, you have to make some changes to support the part testing. It's not just you design and you can test it. So those uh, topics I will cover in my presentation as we go through. So what is the definition of?
Again, you had been mute on mute.
So you are muted.
Okay. Okay. Can you hear me now?
Yes, we
Yes.
can. Hear
Okay.
you.
So I don't know where I got muted because I did not did it. It's automatically happened somehow.
So it seems
Uh,
that by mistakenly someone has muted. So requesting all the participants don't admit the external participant. I am admitting it from the backend. Okay, thank you everyone.
Okay, so a known basically, so you have a device which you want to test. So there should be a known stimulus and then a known expected response. So compare. I mean, you're giving a stimulus and you know what to expect, and that's what you are comparing. So why test basically? So screen out circuits for defects or faults, ensure product quality and reliability level, test data, whatever you test data you collect is used by the design teams and fabrication, basically the factories to improve the technology and the yield. So detect fault at early stage to save costs. So if you detect the fault at early stage, then you are just going to fix it in the next revision or immediately, and you don't ship the bad part to the customer. So detect fault at early stage to save cost. Uh, that's why, I mean, these are the few of the reason why we have to test the parts. Chip manufacturing, because chip manufacturing process is not 100% reliable. Shipping defective parts can sink a company. Logical error not caught until, I mean, 1 million unit recall cost can be $450 million. So this is kind of, if you don't catch the defects early, if you don't test the parts, how much penalty you can have. So this is just a real life example from one of the issue from one of the companies I have picked actually for the example. So these are the some of the common terms used in the test engineering domain. So ATE, what is ATE? It's an automated test equipment. So the equipment is which helps automation on the testing is called ATE. DUT is device under test. So I will use these words. So whatever the device you are testing is called DUT, device under the test. Device interface board or the load board is another term we will use. So device interface board or load board. Some people call it DIP, some people will call it LB. Die is a individual SOC on a wafer. So that is called die. Prober, mechanical unit moving wafer under the test. So when you don't have the packaged part, it's raw wafer. So that to handle the wafer, there is a equipment called prober. Once you make the cut the dies in the wafer, make it in a package part, then to move that package part, you use equipment which is called handler. Binning is sorting of devices based on the test result. So you have a good die, you have a bad die, so that is called binning. So good die will be called bin 1 and some bad die will be called bin 8. So the people segregate the die. If you have like different performance based devices, there will be multiple binning for different speed and performance basically. So binning is used for that purpose on the test engineering side. Why there is a need for the ATE? Basically, people think, oh, we can test on the board. So there are validation boards or there are boards where you can put the parts. So why there is a need for the ATE? So first thing is automation of the task. Second is help in shorter time to market. Achieving repeatability, accuracy, and correlation of result. You can test across voltage and temperature. Can be used across variety of the products. So you don't, I mean, same ATE can be used on the different products. You don't need to buy a new one every time. What test we can do on the ATE basically. So functional CG you can do, you can test the DFT scan patterns, limited functional validation you can do, memory tests, minimum voltage detection, finding the speed, Fmax operation, and Shumu plot. Shumu plots I will come later. So what is this? You will hear sometimes the term called Shumu plot. So what is the Shumu plot exactly? And obviously handling the CQIs. CQIs are customer quality incidents. So if you have some bad part at customer end, so how you handle on the AT. So these are the few whys and where AT can be used. These are just few why and where. There may be more use cases. So there are major ATE, these are the major ATE companies which manufacture the ATE. So Advantest is one of them. Teradyne is another. Then there are LTX, Kriya, Chroma. So there are many of them, but typically, I mean, Teradyne and the Advantest are the most popular in the industry with all the most of the semiconductor companies I know. What is ATE? So it is basically a collection of high performance test instrument controlled via a computer. So ATE consists of electronic systems that generate signal, applies test pattern, sets them in an appropriate sequence, and then use them to test the data. So it is basically you have like all you see in your lab, the scope, you see function generator, you see power supply. So AT is a collection of all those equipment in a single instrument with single equipment basically, and which is controlled obviously by the computer. So some testers are ATs are Linux based, some are Windows based. So it just depends on the vendors to vendors. So this is how the typical AT looks like. So some are as big as your small, they fit in a small 10 by 10 room size roughly. So picture may be not telling you, but these are approximately size of, and they can be as small as they fit in your desk, basically in the office desk also. So the popular ones or the production ones are typically fitting in a 10 by 10 room kind of minimum space they need. So this is the middle picture is Teradyne Ultraflex tester, and the right side is the Advantest 93K tester. So what are the component of the test system? So you see in the picture, you see there are, it's like there is a chassis, there is a thing protruding outside, kind of a hanging thing. So there are many components in this overall kind of tester ATE. So test head is one of the component. Then computer will be there. DC subsystem, your all the power supplies, DC meters. AC subsystems, your automatic waveform generator, digitizer, and then digital subsystem will have clock, pins. So this is the basically architecture of a ATE. So very old picture. I used this picture back in 2000 when I started working as a test engineer. I'm still sharing the same picture. The architecture has not changed at all. It just the kind of shapes and the speed, everything has changed, but architecture of the AT still remains same. So you have a computer, you have a power supplies. So there are power supplies, then DPS for VDD, VIL, VOH reference. So device power supplies. And then these system power supplies are for the supplying power to the system, but DPS are actually power supplies for the SoC. And then you have system clocks. So to provide the clock to the SoC, pattern memories, whatever kind of pattern you want to put on the SoC. So there are pattern memories, then time formatting, formatting the signal basically. So how much you want to delay one pattern, or what is the uh, clock frequency, clock width, all those, or data width, formatting, timing, formatting, and masking. There is a unit. So and then special tester options. So some devices may have RF or more memory. So there will be special tester option to test the special devices. Then precision measurement unit. I will come in detail on all these things. Precision measurement unit, and then there is a test head where your pin electronics cards are, and then there is a load board. I think I covered it before. So load board is where you basically input your chip or SoC, and it connects with it interface as a connection between the test system and the SoC. So that is the load board. So a load board or the device, a DIB is a device interface board. So load board or device interface board. So as name suggests, how to interface the device with the ATE. So that's where the load boards comes in the picture. So has circuit board designed to serve as an interface between the ATE and DUT for the packaged devices. So routes the test and response signal between the DUT and the ATE. So this is how a typical load board will look like. So one is for the 93K, and then one is for the Ultraflex or J973. I don't remember which one is which, but so either it will be square or rectangular, or it can be any size. But these are the typical two for the standard testers we use in NXP. So there is a test socket you are seeing here. So the test socket is because we have to change the parts many times. So there is a socket where you can open the socket and put new parts. So this is to test it manually, basically. So you are seeing, and you are seeing 4 sockets in one of the boards. So you can have you can test basically 4 parts in parallel. That what this 4 sockets means, you can have test 4 part testing in parallel, and this number 4 can go even 16, it can go to 32. So it depends on the how complex the SOC, you can test that many SOCs in parallel. So that's what the ATE helps you. So you can test. So I have seen personally worked on parts where we are testing uh, 64 parts in parallel, but people are testing few hundreds part in parallel, even in NXP. So it's like 64 to, it can go from 1 part to few hundred parts in parallel, basically. So it all depends how complex the part is. And then the next thing is when you want to test the wafer. So the prober, we use a machine called prober. So prober is a complex machine that moves wafers, actually. This is how the prober will look like. So the test head from the ATE is attached to the prober, and you can put the wafer on the prober, and it can uh, move the dies around, and you have a connection between the die to the ATE, basically, and you can test. And that then prober are also, I mean, so there is a load board or probe card. It is called probe card on when you are testing the wafer. So probe card can also be either for a single die, or it can be multiple die. So currently, like uh, you can have 24 dies together you are testing at one time. So that is called parallelism, basically. So more the parallelism, more you are efficiently using the ATE. So if you are testing 24 dies together, that means in same time, like if the test time is your like 10 seconds for one die, if you are testing 24 dies, then your effective test time become 0.24 seconds per die. So that's where the parallelism comes important. More die you test together, more you save. So these are some of the prober manufacturers worldwide, just for your reference. Then this is the handler picture I'm showing. So the handler is a complex machine that moves the package device. So there is a wafer which when cut and make a package part. So to test the package part, there is another unit which is called handler. So handler is again, I mean, you can test multiple parts together, like 2 parts, 4 part, 8 part, 16 part. I mean, it depends again the complexity and everything. So handler is used to test the package part, and prober is used to test the wafer, basically. Okay. So this is a closer picture for the probe card. So this is in the left hand side, this is the wafer. So wafer has the pads, basically. So you to connect to the wafer to the ATE, you have to connect the die pads to the ATE. So how that connection is made? So the probe card is used basically for that purpose. So a probe card is a circuit board designed to serve as interface between the ATE and die. Die is an individual chip on the wafer. So there may be 3,000 dies, 4,000 dies, depending on the size of the device in a wafer. So how you connect that die directly without packaging to the ATE to test it? So probe card is used, basically. So probe card routes and the test and response signal between the die and ATE. So you see the right hand side picture. So there are needles, basically. So these needles connect to the pads of the SOC or chip in the die. So when it connects to the pads of the SOC, then you can send the voltage or clock or data, whatever you want, and you can interface with the ATE. So we talked about component of the ATE. So what are the, I mean, how it is different from the regular bench? So it is like collection of the equipment. So what are the equipment there you can utilize to test the SOC? So first thing is the PMU. So PMU is nothing, it's called precision measurement unit. So you can force it's a DC measurement. You can do forces current and measure voltage, and vice versa. You can force voltage and measure current. Range setting, ensure accurate test results. So you can have multiple ranges. So if you are testing as SOC with a lower voltage, so you can select a lower range which has more accuracy. If you are testing SOC with like 5 volt, then you can select higher range. So it has various ranges basically. So you can select the range based on your accuracy you need for that particular voltage or current. So limit setting, you can set upper and lower limit. Clamp setting, you can set the clamp for the voltage and current so that you don't accidentally burn the part. So you can set like 2 milliampere is the clamp. So the voltage will not, sorry, the 2 milliampere is the current clamp, then it will not go beyond that. Similar like it is if you're like 1 volt is the current voltage clamp, then the whatever you accidentally even program or chip has an output of more than 1 volt, it will not go beyond that. So you can clamp, you can set your limits based on the range or accuracy. So all these functions PMU can handle, and that's inside the ATE. So test program development consideration. So how you decide, I mean, which tester or is suitable for your device. So basically, there are few things we look when we choose the right ATE, because ATE is very actually costly equipment. It's not like you can buy as much as you want. So it is very costly equipment. It has a lifespan. So we have, and that is it is dictating the cost of the chip also. So how we come that to a conclusion like this ATE is needed for this particular chip, or what is the configuration of the ATE needed. So max device, so there are kind of few parameters, I mean big parameters which dictates is like max device speed versus max ATE speed supported. So if you want to test a like 500 megahertz part, so you have to have ATE supporting the 500 megahertz. You cannot have a ATE which just supports 250 megahertz or 400 megahertz. You cannot test a 500 megahertz parts on that. So you have to have that thing in your mind. Then obviously the power supply uh, and the pin, how many pins the SOC. If SOC has like 500 pins, then ATE must have more, or at least the minimum that number of pins on the ATE. So, and then availability, system availability, whether it's easily available, what is the support, and then I mean test cost versus device cost. So device under test cost. So if your SOC just sold at $5 and your test cost is like $3 or $2, then it does not make sense at all, because you are spending most of the money on the testing. So you should choose a ATE which suits the device budget, basically. So we cannot have a high-end ATE and testing a very low cost.
Sorry, Nred, someone has muted you. Please unmute yourself. So requesting other member, please don't admit the external participants. I am admitting from the backend. Please requesting member request. Please don't admit. I am admitting one by one. Thank you.
So where I got muted. So test cost versus the debt cost. So I was talking. I don't know where I got muted. So basically, your how you define like what ATE you need for your SOC is also dependent on the cost of the SOC you are selling. Uh, so if your SOC is kind of selling at $5, you cannot afford a ATE which like takes $2 to just test the SOC, because otherwise you cannot be competitive in the market. Okay, so that's what I was telling. So these are the few factors. I mean, we keep in our mind when we are deciding, okay, this is the SOC we are going to test, and then what is the ATE which we are going to choose. So typically, I mean, we have uh, different options. So we will define the ATE configuration based on the cost, based on the speed, based on the SOC power and pin, and how easy is the availability. These are the primary consideration before going deciding like this chip is going to use this ATE. And the tester memory. So how big your patterns are. And so if your SOC is really big, then the pattern you have to store your stimulus basically in the tester. So how much the tester memory you need. Okay, so there is a quiz. So what is an ATE basically? So I can see, I can chat response. So people can type in, I think, their answers. Wasim, can they type or on the window?
Hello?
Wasim, can they type on the window? Participant can type in the window or no?
Yes, participant can type in their question in the chat box.
Yeah, so I want participant to answer this question if they are attending. Some people are joining late, but those who are attending from the beginning. So what is an ATE? I mean, I talked so much, so I'm just testing. I mean, whoever is there.
Yes, I can see people are answering. Most of the people are answering B, option B.
Yeah, automated text equipment.
Okay, good. So that's the correct answer. Next question is, what is the purpose of device power supply? We start with a new answer. Okay.
I think here the answer is all top diagram.
What is the answer? Okay, I'll go ahead. So it's A. Okay. Okay, next question. Anybody knows the answer?
Yes, people are answering. The few people have answered option B.
No.
And, yeah.
It's actually answer A. Sorry, answer C. So the probe card is answer B. Probe card is the interface between the wafer and the ATE. The load board is the interface between the packaged part and the ATE. Okay. And handler is to move the parts around which you are testing basically. So now I'm coming to the manufacturing test flow basically. So I mean, you have heard people, I am working in the design team. So people, once the design is complete, so what happens after that? So people work in verification, validation, or test engineering or DFT. So what happens once the design is complete? So the GDS is sent to the fab, whatever the technology it is, C90, C55, C40, and then fab develop the reticles. So fabs are like ATMC, TSMC, UMC. So they develop the reticle, and then a wafer is made basically. So it can be 200 wafer, 300 wafer. So once we receive the wafer, then it comes to the tester basically, which is ATE for testing. So then it will go first to the prober. So we talked about prober first in the previous slides. So it will come to the prober. So prober will probe the complete wafer. So if like suppose this wafer has 5,000 dies, so it will probe all the dies, and then probe level testing is done and good dies are identified. So you see the green and the red dots basically. So I mean, in old days, the prober used to ink the dies basically. When I started first time in 2000, then the dies were inked at that time. So there will be a black dot on the die. So bad dies basically. Good dies will be not touched. So that's how the manufacturing knows that which die to assemble, which not to assemble. Now it's all more automated. So it just like the map is generated and it is stored in the file, and the same file is loaded in the assembly site, and then they know which dies are XY coordinates. So there will be a center coordinate, and then there are XY. So you know, like second die on the x-axis and fifth die on the y-axis is bad, so you just don't take that die, pick other die. So once you have probed the good and bad all the dies, then good dies are picked and then packaged after the probe. So you will have this packaged SoC basically, and then they are put into the final test. So this is a handler, so you put all the good dies on the handler, and then you test on the ATE, and then you have the good parts went to QC, and then parts are shipped to the customers. So this is the full flow once you design a chip, and then how it goes through from the manufacturing to the customer. I talked about Shumu plot in my previous slide. So what is Shumu plot basically? So I don't remember how the Shumu name came. It's actually I think some animal or something, if I'm correct. So
सर कौन सा subject है
again,
सर
somebody has a
सब्जेक्ट
question.
कौन सा है
Subject कौन सा है? It's a ATE SoC test basically. So
ओके सर
vital role. It plays vital role in debugging and CG. So CG is characterization. So it plays if you have to debug any fail and you have to characterize the part, then it plays a vital role, helpful to point the electrical failure in a circuit under test. So, and if there are any electrical fails in a circuit, you can it helps to point out. Test pattern is tested under different frequencies, process, and voltage at various temperatures. So, and the results are captured in form of logs and Shumu plots, which are further analyzed for RCA. So if you have to see that whether your part works at which frequency, so you can do that by the Shumu plot. So you are one side, it is a voltage. So on the y-axis, if you see there is a VDD, and on the x-axis it is the frequency in the gigahertz. So you can run a Shumu plot to know, I mean, what is the maximum frequency your part works at a certain voltage. So you see, I mean, sometimes you have the same part sold by companies at a higher price point or lower price point. So they use the binning a kind of this Shumu plot mechanism and check, oh, this. So if my part works at 1 volt at this particular frequency, then it is like 1.2 gigahertz part. And now the same, some parts does work at 1 gigahertz, so they sold at a lower price. Uh, 1 gigahertz or 800 megahertz. So you can speed bin basically the parts. And then when you are debugging, you see this on the right side. So the left side Shumu is a clean Shumu where you see the higher the voltage, the lower the, sorry, lower the voltage, lower the frequency of the part is. But on the right side, you see there is a red line in between. There is a red which is in a circle. So that means you have some issue with the part. So part is working good. So green is good and red is kind of fail. So there are lines here. So that means part is working on some of the zone and it's not working in between at certain voltage and temperature. I mean, it is I think frequency and voltage again. So certain frequency it is not working. So it may happen at a temperature also. So you can typically we test at minus temperatures, room temperature and hot, depending on what profile we are selling the part. So you once you run the Shumu, you know, okay, so I don't have a clean Shumu. That means there is some issue. And then you root cause the fail, why it is failing at certain location. Is there a timing violation or whatever it is? So you work with. First, you look, I mean, it is a pattern issue, tester issue. Other, if it is not, then you work with design team to figure this out, why it is failing at certain frequency or voltage. So that's how the Shumu plot can help. So Shumu plots can be 2D or even you can have 3D. So you can have 3 parameters. So you can have voltage, frequency, and then you can have another AC parameter basically, or voltage parameter if you think that that is also a dependency on this plot. So you can have either 2D Shumu or you can have even a 3D Shumu basically. So what is the next topic is how we decide the optimal voltage for the testing. So if you, I mean, test that. So there is a minimum voltage, there is a maximum voltage, there is a nominal voltage. So how we decide that which is the right voltage to test. So if you test like too low, then you will have test related yield loss. If you test at very relaxed voltage, then there are chances that you will have CQI or the PPM basically you will have fails. So there is a fine tuning we have to do what voltage and frequency we are testing the parts basically. So it so so there is a customer specifications voltage level supply, then voltage level monitors are there, then there is a chip or pattern specific IR drop, then tester supplies have some inaccuracy. Even, I mean, we say it's very accurate, but still there will be, every instrument has some inaccuracy. Then how the LV and HV corners are sign off, test voltage. So this all feeds into the final basically Vmin and Vmax at test. So test voltage are derived using formulas considering multiple aspects shown. So we consider all these aspects basically, and then uh, we decide, I mean, what is the minimum voltage we have to test and what is the maximum voltage we will test. So, and this can change on the probe at final test and quality check. So we do, sometimes, I mean, we don't have the same voltage or frequency at the probe. It may be different at the final test versus the probe. So it all depends on these few parameters, we come to exactly what Vmin and Vmax we are going to test. So next thing is what are the design changes need to support ATE? So ATE, I mean, you can test the parts, but there is a support needed from design side when we are designing the parts. So DFT infra is needed. So you have the chip should support the DFT infra to find stuck at and continuity fails. Memory validation infrastructure for checking on-chip embedded flashes, SRAMs, DPRAMs, fuse blowing for various trim values, SoC versions, and any customer specific requirement, ability to access all the registers on SoC. I mean, if you don't have ability to access, then you cannot obviously test them. Ability to download code into on-chip memories to support the FMAX operations. A tester works on a deterministic mechanism. So in order to remove indeterminism, you need to have a bypass mechanism for the PLL clock, debug hooks to help in debugging fails, and timing closure as per AT guideline to remove indeterminism due to synchronization logic. So these are, because this topic is more on AT, so I'm not covering in depth, but these are few of the design changes needed to support ATE, and typically, I mean, every SoC has all of these covered, and there is a guideline goes to the design team from the test team that these are the things you have to take care. What is support needed from the verification side? So pass-fail criteria of pattern should be visible on IO pin. So I mean, if you have something internal which you cannot visually read or write, so you cannot decide the whether the chip is pass or fail. So you should have a pass-fail criteria visible on any of the IO pin, basically. There should not be any forcing inside any SoC. So if you any forcing should be IO level, because tester cannot force signals inside an SoC. It's not a verification where you have access to the RTL and go and force any signal. The results of the pattern should be deterministic and repeatable. So tester is comparing with the known response. So your known response, so it is comparing with the known response. So your result of the pattern which is coming as an output should be deterministic and repeatable. For power measurement, the pattern should put in the infinite loop max low voltage stage as attained for. So if you are measuring the power, you need some time. So pattern should put the part in infinite loop, whatever the state you want. Pattern need to start executing after PLLs have logged. So if your PLLs are not logged and you are already, your output is coming, then PLL log time could vary between simulations. So because PLL lock varies between chip to chip, so you should have at least a minimum max time you think the PLL will take to lock, because after that only the output is deterministic. So these are the few things we talked from the verification side and design side to consider when people are designing a chip so that ATE can be supported for that chip. So I think we have a few minutes left and I'm open for any questions.